speaker is Nicolas Durrande, who is working at Prowler.io, and he's going to be making emphasis also on how we design these kernels and maybe trying to solve the questions that people were asking before. So thank you.
Try to. Hi, everyone. Yes, I will be giving a second introduction. Some of the things will be repeated from what Rich said earlier, but like having 2 points of views on things is always helpful to make up your mind and get a better understanding. So I'll try not to spend too much time on it, but still to give a few more material. And and then I will be talking about how you can build covariance function for specific needs. And let's get started. So the PDF of a Gaussian random variable is just the exponents of minus something that is quadratic, and the distribution is fully specified by a mean that is a scalar and the variance that is a positive scalar, right? There's nothing new here. And when it comes to multivariate Gaussian distributions, then the definition of a multivariate Gaussian distribution is a random vector. So now each draw is not just a scalar value, but each draw will be a vector with values in it. So you throw a dice and you end up with several values. And we say that this random variable is Gaussian if any linear combination of the components of your vector is something that is Gaussian distributed. That's the definition. So that's two examples of samples from a multivariate Gaussian. And that's one counterexample. So this is not a multivariate Gaussian. If you look at the distribution of y1, it is. If you look at the distribution of y2 as just a scalar, it is also something that is normally distributed. But the combination of the two, like this vector, is not Gaussian distributed. And you can tell that like the contour line of the density in here are not going to be ellipsoids, right? This is not the exponent of something that is quadratic. So having all components being Gaussian is not enough to say, oh, this is a multivariate Gaussian. So that's the same expression Rich gave earlier. And this is just the generalization of the 1D case, because if you replace this covariance matrix by just a scalar value that is the variance, and if you replace the mean here that is a vector by just a scalar value, you end up with the exact same expression as we have in 1 dimension. And if we look at this distribution, it's parameterized by the mean that is now a vector and the covariance or the variance that is now a matrix instead of just being a scalar value. And previously, we've seen that the variance is something that is positive. And for a covariance matrix, it has to be positive semi-definite, so it has to satisfy this inequality. So this being positive semi-definite is the equivalent of saying a variance should be greater or equal than 0, right? It's the exact same condition. So what about the conditional distribution? So you've also seen that before, so I will cover that quite quickly. We know if we apply the product rule that the distribution of y1 given y2 is equal to the joint distribution divided by this renormalizing factor that guarantees that this probability density function will integrate to 1. And if we look at, if this is jointly Gaussian, then this will be the exponent of something that is quadratic in y1 and alpha. The term in alpha, I can just put them into the constant if I want to, and I just end up with something that is quadratic in y1. And I said earlier that something that is exponent, something quadratic, is a Gaussian PDF. So the conditional distribution is still Gaussian. So we can look at this on this figure. I have the 2D density. Now if I fix the value of x2 to one value, so what's the distribution of x1 given that x2 is equal to this value? This is equivalent to taking a slice into this multivariate distribution. And if we look at just this slice as a one-dimensional function, then we can see this is still Gaussian distributed, right? And that's another example for a 3-dimensional Gaussian vector. So now each sample is a point in a 3-dimensional space. So it has 3 components. And if I fix the value of y3, so if I observe y3 is equal to this value, and I look at the slice of the conditional distribution, I end up with here something that will be a bivariate Gaussian distribution. Fine? So that's, I put them here because they are important, but you've seen that in the talk just before. There's nothing different here. So we can get an analytical expression of the conditional mean and of the conditional variance of a multivariate distribution. And yes, and now we'll be talking more about Gaussian processes. So for a Gaussian process, each draw you get will be a function. So you throw a dice, and on each side of the dice, then you end up with a little function, right? So that's a random process. And we say that a random process is Gaussian if for any points you select in the input space, the distribution you get for this vector is multivariate normal, right? That's slightly different words, but that's the exact same definition Rich gave earlier. So let's have a look at that in here. So that's samples from a Gaussian process. And now if I fix a value of x1 here, a value of x2 here, and if here I represent the GP evaluated at x1 and the GP evaluated at x2. So for one sample here, these 2 points will be 1 point over there. If this is a Gaussian process, then these guys will be distributed as a Gaussian process. All right. So if I take the 2 points to be close by, then I find that the two values on the right are extremely correlated, right? Because the points are close by, so the values taken on this curve by these 2 points, they can't be really different, right? They have to be very close one to another. And that's why we find here a very high correlations between these points. And on the other hand, if I put the 2 points to be very far away one from another, then there's basically nothing that links the value of the GP at these 2 points just because they are far away. All right. And the function that will tell us how much these two evaluations of the GP are related, so what is the covariance or what is the correlation of the two things on the right, so how these depend on the locations we choose here, that's the covariance function, the kernel. Any question on that? Yeah.
What was on the right graph? On the right so yes, isn't the matrix supposed to be like not binary?
So for each sample I have for my GP in blue here, it will have one value in it will have two values, like each time it intersects these two locations at x1 and x2. Right, so these two values, I represent them here as on a two-dimensional graph. So let's say like this point here is at -2 and -2.1, and that's probably like this point.
So this is correlation matrix
No, so on the right it's not a correlation matrix, it's just a scatter plot of the GP evaluated at two locations. So I'm doing it with two locations over here, but I could do it with more like 4, 5, 6, but here I would end up with a higher dimensional cloud of point, but it will always be Gaussian distributed. Yes?
What did you use to make this? This is really nice.
Yeah, so this is made with Bokeh, which is you write code in Python and then you can make an interactive graph. I struggle the first time I've been told B-O-K-E-H, Bokeh. And yeah, in the background, it's for the GPs, it's GPFlow2 that I've been using. GPFlow library that I've been using. Yes?
If we were to fit the line to the right-hand side plot, the slope of that line, does it correspond like just numerically to something that you set up when you simulated the process?
Not quite. So the correlation will tell you how wide this is, but the slope depends more on the ratio of the variances of the two variables and on the correlation. So if I keep the same correlation, but if I increase the variance of one of the variables, then this is going to affect the slope.
Right. And in the kernel that you use to generate the Gaussian processes, these constants are where?
I'll come back to that later, but I have, or maybe I can answer now. If I put the 2 points at the same location, so if I only consider, come on, never mind. If I only consider one location, that I will have one variable that is Gaussian distributed, and this variable, so I have this in.
That's essentially why I have the question, because if you overlap them, then you have a diagonal line, so sort of one, so the correlations won't.
Yes, so if I overlap them, you can say I just have like 1 point. So I will have my GPZ in x1. So this is just one random variable. And I can compute the expectation of this random variable. And in this example, I choose something that was 0. And I can compute the variance of this random variable, and this will be given by the kernel. This is I have it on this.
Don't correspond to anything from the plot, right?
So to okay, maybe I can be more specific. Is it clear how I generate the samples from the GP? So I start from so if I want to generate if I want to plot a function, I'm going to take a grid in the input space. Then I'm going to generate the values of the GP at that point of the grid. So the values of the GP will be multivariate normal. I have to choose what mean I want and what covariance function I want for this. But this is going to give me a mean vector and the covariance matrix, right? And the mean vector here is 0, and the covariance matrix is given by my covariance function, my kernel, evaluated at my grid points.
Maybe I can ask after, sorry.
No, please.
Well, it just seems intuitive that, like, as you move them apart, we see the scatter plot, like, losing structure.
Yes.
So if I were to sort of pick a line through that cloud, it presumably have kind of like a slope 0. So that's 0. If I think of like the
It's
matrix that generated.
so you can't really say you have, if they are independent, you can't really say you have a slope 0, because basically any line, your data is a circle, right? So any line, you could say the slope is 0, the slope is vertical, or there's just no dependence between them. So there's no, the slope 0 doesn't fit the data better than any other slope. That answers the question?
Yeah, I think my intuition is just wrong. Yeah.
Don't those are tricky things, don't worry. We
the off diagonals of the covariance matrix kind of
That's what
set that shape.
That was my intuition. That seems like no.
So for multivariate Gaussian, the distribution was specified by a vector and a matrix. And now for a GP, the distribution will be specified by a mean function and by a kernel function. So the mean function is something pretty simple. It's just for every point x, it tells you what is the expectation of x. And the covariance function is for any couple of points. It tells you what's the covariance between these two guys. So that's why I wrote that on the board before, because the variance of z of x is equal to the covariance of z of x with itself. So this is equal to, if I have one here, I should be consistent. So this is equal to the kernel. So that gives you the kernel at xx will give you the amplitude of the GP at x, basically, right? So for the mean function, we can pick whatever we want. So the function doesn't have to be continuous, or it can be any function. But for the covariance function, it has to satisfy some property to ensure the consistency between all the marginal distribution we are specifying. And the two things that need to be satisfied by a covariance is given by Love's theorem. So it has to be symmetric. K of xy should be equal to K of yx. So this is just because a covariance itself is something that is symmetric. So since the kernel is a covariance, it has to be symmetric. And it has to be positive definite, just because if we pick whatever subset of points, we know we should have a multivariate normal distribution, and a multivariate normal distribution should have a covariance matrix that is positive definite. So there's no, like, it's not new conditions. They are like very natural. They all come from the fact that a variance is something that should be greater or equal than 0. So proving that a function is positive definite is something that is quite tricky, just because we would like to show that this is positive whatever the number of points we consider, the subset of points where we evaluate the GP, whatever the location we choose in the input space, and whatever the coefficients alpha we put in there, right? So a direct proof that this is greater or equal than 0 is usually not possible. We'll see two special cases where we can actually prove it later on. But if you open books on Gaussian processes, then you will see that there's plenty of functions that have already been studied and that have already been proven to be positive definite. So you can pick any of these functions, and you can generate samples from a GP that has this specific covariance. Okay, and we have typically two parameters in this, one that is called the variance and one that is called the length scale. So the variance is typically a parameter that is in front that will tune like the vertical amplitude of the kernel, and the length scale is something that will divide the input. So it's also a rescaling, but a rescaling of the input space. All right. Okay, so that's some examples of samples for this specific covariance. So here, that's a Mattern 5/2. As Rich was showing before, if you change the covariance, you can end up with very different regularities for your samples. So here they are very wiggly. You can't differentiate these samples. Yes?
Will there be links to these interactive examples?
Yes, so this one is available on my GitHub, and for the other app I was using before, I'll put a link. Yeah, it's not available yet, but I'll put a link. So depending on the covariance you choose, you end up with samples that have very different properties. So here, for example, you can see that the covariance is exponent minus a distance, so not something quadratic, just a distance. And if we just add a square to the distance here, then the samples they become very smooth. And now if we start tuning the length scales, so it used to be 0.1, no 0.4, 0.6, so they become less and less wiggly, right? We have lower and lower frequency when we increase the length scale. That's just because when we increase the length scale, we are dividing here by a quantity that is larger and larger. So this distance, this rescale distance is smaller and smaller. So points that are far away, after being divided by a large number, they appear to be close by inside the exponential. I said nothing complicated here. And if we increase the variance, so from 1 to 5, if you can see here, the range changes. So that's just a rescaling of the vertical axis to change the variance parameter. Any question on that? No? Keep going then. So that's some examples of covariance functions you can get in GPFlow, for example. You have pretty much the same one in GPy or in other toolbox. So you can see they can look very, very different, right? They are not all like hat shaped like these guys. It can be just a constant function. It's something that is positive definite. You can use it to generate some samples. That's the white noise. So the covariance between the GP at one point and the same point is 1 in this example, but it's 0 as soon as you move one of the two guys. They become independent. You can get kernels that are periodic. That's two different examples. Just the linear kernel, Rich was talking about earlier. So x times x prime is something that is positive definite, or you can get a polynomial or arc cosine like this. A lot of kernels on the shelf we can be using, and they all imply different properties for the samples. So that for the same covariances, the kind of samples we get. So we can see that the periodic kernels, they end up with periodic samples. So that can be some interesting behavior if you know that your data comes from something that has some periodicity in it. And yeah, so there's a lot of kernels on the shelf that correspond to a lot of different priors for Gaussian processes. And now let's talk about Gaussian process regression. So now we have some data. So for some location x, we have observed the value of the function we are interested in modeling. And now we would like to predict what's happening when we are outside of these points we have already observed. So if we don't make any assumptions, we can't make any model, right? Modeling is taking some data, making some assumptions about it, and then using these assumptions to get some information. So the assumptions we are going to make is that this data comes from a function that is one sample of this Gaussian process, right? And now if we combine these two informations, so if we combine the data and this prior we have on our function, we can get a posterior distribution of the GP, and we know that this posterior distribution, we have access to it analytically. So we can compute what's the conditional mean of the GP given the data we have observed, and we can compute what's the conditional covariance. And this is the way the posterior looks. All right. One other way to look at this difference between prior and posterior is to say, this is my prior, and when I throw the data in, I know that like in this location x, the value should be 0. So in here, I'm going to get rid of all the samples that do not go through exactly these points. And we have an infinite number of samples, and we still have an infinite number of samples that go exactly through this point. And we can do the same for all the points we have over there, and that gives us like the filtration point of view of what's a posterior distribution. We just get rid of the elements of the prior that are incompatible with our data. And yes, so but in practice we don't throw a lot of samples and get rid of the one we don't want, because we have an access directly to the posterior distribution. So computing this is pretty straightforward. So here, that's the vector of the covariance between the points where we want to predict and the observations we have. That's the covariance matrix at the observation that we need to invert times the vector of the observations, and that's basically the same terms as we have above. So what about the complexity of doing this? So this matrix will be as big as the number of observations we have. So the more observations we have, the more costly this will be, right? But this, yeah. And so we need to store a matrix that is n by n, where n is the number of observations. And we also need to invert this matrix, or in practice, we don't invert the matrices. We compute the Cholesky decomposition of this matrix, and we do two triangular solve because it's numerically more stable to do so than just inverting the matrix. But computing the Cholesky as and doing the triangular solve as the same complexity as inverting the matrix. It's n cubed, where n is the number of observations. So we have two different types of complexity: the storage footprint that is n squared, and the complexity that is n cubed. So on a regular computer, that means that the maximum number of observations you can handle with plain GP regression is somewhere between 1,000 and 10,000 points.
Sorry.
Yes.
Could you go to the previous slide? There's something, but for the covariance, should it be kxxx, so only for the vectors we're predicting, minus kx large x and then k large xx? I don't understand where
Okay.
the y is coming from.
So the question was, why do we have a y in here and why don't we have just x? This is a conditional covariance, right? So a covariance takes two inputs. If you replace the y by the x, you're just computing the conditional covariance between 2 points that are the same, and that's the conditional variance. So if you're just interested in the variance of your prediction at one location, then this location, say x, you should compute C of xx in here, and that's the conditional variance. Here I'm specifying the full GP distribution.
Yeah.
Any other question? Yes?
I think it was the previous slide, or the one where you have basically the visual with the restricted quantity condition.
Yes.
This one. Oh, I see. Never mind. No.
So this is still a GP, and its covariance is given by exactly what we had before.
Oh, actually, yeah, I do remember the question. How do we choose which lines to sort of plot? I mean, in what sense is this a confidence interval or something?
So this is not confidence intervals, that's just samples from the model. So you don't know which one of these is your function, but you know it should be one of these, and again you can sample an infinite number from them. Yes.
Like along that same point, where in the math does it help drop that out? Drop the ones out that don't fit the data?
So
If you come to it later, you can explain. Yeah, this is explain now.
So in the math, you see that when you look at the conditional distribution, because that's when you apply Bayes' rule, basically you have the, Rich was saying, like, how surprising your observations are. So this is something that will reweight your new distribution to make sure it integrates to 1. And then you also have this like joint probability of what you have observed and what's left and unobserved. So this is the bit that will do the reweighting. So that's the math behind are exactly what's the conditional distribution of a multivariate normal, like the one we did, where you have a Gaussian distribution and then you take a slice through it and you renormalize this quantity. That makes sense? Yes?
So the observations, the uncertainty collapses down to the measurement uncertainty.
Yes. On this example, yes.
Go back to the conditional covariance, or zero covariance.
Yeah.
What exactly, how does this translate into that equation? Like, what becomes...
You are 2 slides ahead of me. I'll come back to that. Okay? So I'll just finish on the complexity. So yeah, the maximum budget is around like 1,000 to 10,000 points. If you have more data, then you'll have a talk this afternoon from Denhan that will show sparse GP methods. And if you want to be faster than this complexity that is n cubed, then we will have a talk on Wednesday by Arnaud that shows how to use state space models in the Gaussian process framework. So this is a plot with the confidence intervals I think you were referring to. So in each location here, since we have a GP, the distribution is Gaussian. And it has a mean and it has a variance. So here, for each location x, we can represent the mean in a thick line and 95% confidence intervals. So mean plus minus twice the standard deviation.
I was asking about that because I find that to be a misleading visualization.
Okay.
Because not every function that falls within the shaded area is fair game.
Is?
It's not every function is fair game. It's
Yeah, so this is everything according to your initial assumption that you have this prior that has this specific covariance, and then that gives you a posterior distribution given these specific values, right? If you want,
Of the functions.
yes.
And I was just thinking to myself, this sort of shaded area makes me at first feel, well, then anything within the shaded thing is fine, but it's not.
No, that's right. That's why it's nice to look at samples. You have much more information when you look at samples than just looking at this. So now to answer the question you had. So a few properties of Gaussian process regression. So the one we've seen so far, they interpolate the data points. So can we show why this is true? So we have the mean. So let's say we want to predict at the first observation point, right? This is going to be k of x1 x k of xx minus 1 times the vector of observation. So remember, this is a vector, this is a matrix, and that's a vector. Now if we look at this matrix here that we invert, the first line of this matrix is going to be the covariance between the first observation point and all the other ones, right? So basically, this line here in the matrix is exactly the line we have over here. So if you look at that, we have like a vector multiplied by the inverse of a matrix, and this vector corresponds to the first line of the inverse. So this product here has to be 1, and then the 0 everywhere times the vector of observation f. Right? When you multiply a matrix by its inverse, you end up with the identity matrix. So if you multiply the first line of the matrix times its inverse, you will end up with the first line of the identity matrix, which is this guy. So this product will just select the first value we have in our observations. So that's f1. So here we've just shown that the mean predictor is going to be exactly equal to the value we have observed over there. All right. Now we also need to show that the confidence intervals, they also collapse to 0. And it will be exactly the same trick. We're going to have k of c of x1 x1. So what's the conditional covariance at our first observation point? K of x1 x k of xx minus 1. And that's the exact same trick as before. This is going to be 1 and then zeros everywhere else. We are going to multiply that by this vector. So we're going to pick the first element of this vector that is exactly this guy. So this is going to be k of x1 x1 minus k of x1 x1, and that's 0. So the conditional variance where we have an observation is 0. So that's why our model, they interpolate the data points, and they know that they interpolate. Like the prediction variance is 0. They are sure about the value there because you just gave them one observation point. Right? Second question, the prediction variance does not depend on the observations. Well, there's nothing to prove here. When we look at this expression, the observed values f, they don't appear anywhere. The mean predictor does not depend on the variance parameter. So you remember the variance parameter we had in front of the covariances. So if I'm a bit more explicit about what the kernel is to make this parameter appear, m of x is going to be sigma square times times the vector of observation. I'm just saying here that I'm writing k as sigma square times k tilde. And you can see here that this guy and this guy cancel because this one is inside an inverse. Yes?
Do you have any like fresher pens?
I have others. I'll try this one. Can you still read or? Okay. So yeah, so the mean predictor does not depend on the variance parameter. And the last thing is that they usually come back to 0 when we are predicting far away from the observation. So, or the distribution of the GP comes back to the prior distribution when you are far away from the observations. And this is something you can see in here. When you are far away from the observation, if you have a covariance that is like a hat covariance function, like many of the covariances we were looking at so far, if the point where you want to predict is far away from the observation, this vector is going to be 0 or tend towards 0. This is just going to be a constant, so the mean is going to tend towards 0. And for the covariance, again, this guy and this guy, maybe I should write it again. C of minus 1. So if the kernel is something like that, or if it is something like that, so this is, here I'm putting k of x1, x2, I fix x1 to this value, and I represent this for a given x1 as a function of x2. If these 2 points are far away, this quantity tends towards 0. So if the prediction point is far away from the observations, then this is going to tend towards 0, and we're just left with this bit, right? Yes?
Does the notion of far away, though, depend a bit on the length scale?
It does completely depend on the length scale. So it's the further you go, the more you will tend toward the prior. So we can look at that in one of these examples. So that's one example of a GP model with just 2 observation points. And so we can see that the model interpolates over here. I will show this representation. So the model interpolates. That's the first property we were showing. If I increase the variance in here, the mean doesn't change. So it looks like the mean changed in here, but it's just because the scale here was changing, but the mean doesn't change. And if you look far away from the observations, then you end up with the same. Here the distribution tends towards 0, and the standard deviation are between like minus 3.5 and 3. And if you look at the prior, that's kind of what we had for the prior. But so as you were saying, if I start increasing the length scale, then points that before were far away, they now are kind of close by to the data. We still have a high correlation, so we still have the data still gives us some information about what's happening over there. But if I were to plot what was happening in here, I will come back to the prior distribution. Yes.
Why is the second property called a good property? Like, does not depend on observation. Why is it a good property?
So yeah, so that's quite. It's not a good property. So the question is, so you're talking about the fact that the variance does not depend on the data, on the observations. So so it's not a very good property, but that's a property that Gaussian processes have. It still is a property that can be useful because you can pre-compute in advance what the variance will be even before you had the observations. So on some Apollo missions, they had very, very limited computational power on board. So they pre-computed in advance what will be the variance for the filter that was tracking the landing. So it's not intuitively, you could say it's not a good property, but in practice, you can also use this property, and many algorithms in Bayesian optimizations or things like that do use this property. You will know in advance what will be the variance if you were to do an observation at this location, even without having the value. So in practice, we use it a lot, so we like it. But yeah, but you could claim that you would like the variance to depend on your observations. That's a very good point. Yes?
This is somewhat silly, but could you put 2 points that are close on the x-axis, but very far away on the
Yes.
just out of curiosity?
So I will remove this guy and add one over here. So the scale changed a lot, right? And the model will kind of overshoot, but whatever the data points I give to the model, so now you can see like the range is -150, right? So it has changed a lot. But these models, so we call them non-parametric model because they will always adapt to the data you're throwing at them. So that's something that's a very good property. You don't need to do things in advance. Just you add data, and the model will always have the flexibility to actually fit this data. Yeah.
Wouldn't it be a numerical disaster if you put close points with different values?
Yes, indeed. So if points are very close by, it means that in your covariance matrix, you will have two columns that are going to be very similar, right? And you know that if two columns are equal, it means your matrix has a deficient rank, so you can't compute the Cholesky anymore, you can't invert the matrix. And that's the issues you can run into when you train Gaussian process models, because you have the math say it should work, but in practice you have numerical errors due to metrics that you can't invert. And that's very true if your GP is very smooth, like in this example, or if you have very long length scale, because 2 points that are close by, they will appear to be even closer. You had one question.
So when the observation point is far away from data, the mean tends to the zero because of the Gaussian process has mean zero. But if the Gaussian process has constant mean other than 0, 1, 2, it will tend to this value.
It will tend to the constant mean. It will. What you should have in mind, it returns to the prior when you are far away from the observations. But also keep in mind that's only true for these kind of covariances, right? We've seen covariances like linear covariances or things like that, and that you will not go back to the prior because one observation will have correlation with points that are very far away, right? So this is just for this specific type of covariances. Yeah.
Can you elaborate once more on the fact that the predicted variance is known beforehand, even before observing any data?
Yes.
I didn't quite understand it.
There's
The points there on the plot.
so there's nothing to understand. Just like f does not appear in this expression. So this depends on where you have observations, the
so
x values.
On the input locations that are already set by the data.
Yes.
You don't need to know the y values.
Exactly.
And that is all that influences the predicted variance.
Yes.
But the x points need to be known, of course.
Definitely. Yeah. Yes, we've done all that. So we don't always want GP that interpolates the data points. So sometimes you have some noise in your observations, and it's not because you have one observation that you're sure about the value. You just have an ID, but there's some uncertainty on top of it. And that's something GPs can definitely handle. So if we change a bit the model, and if we say that before we had that the observations were equal to the function we were interested in, and now if we say the observations is equal to the function we're interested in plus some noise, and we take this noise to be Gaussian distributed, then this conditional distribution is still the conditional distribution of a multivariate Gaussian. So it's the exact same math as we did before. We just have this extra term that appears here. That's the covariance you have between your noise. So if your noise, if your observations are independent, this will just be a diagonal matrix you have in here. and same for the variance here. So if nothing changes, just you update one of the term, because now you say that your observation is equal to your GP plus the noise you've observed. Yes?
Does the observation noise have to be Gaussian distributed?
So if your observation noise is Gaussian distributed, then your posterior is going to be Gaussian distributed, and everything is fine. You can compute everything analytically. If your observation noise is not Gaussian distributed, then your posterior is not going to be Gaussian, and typically you don't have a closed form expression for it. So yes, there will be a lecture tomorrow on that from Alan. So here's some 3 examples of GP with uncorrelated noise with a variance tau square. So that's for very small observation noise, 0.001 for its variance. So you can see that the model is not quite certain about what's happening at the observation points. I haven't plotted the observation points in here, otherwise we couldn't see the fact that the confidence intervals were not collapsing, right? But you have to imagine there's the same observation points in here. So the model is quite certain about what's happening, but not completely sure. And the more observation noise you have, then the more uncertainty you have in your predictions, because you give less and less observation, less and less information to the model, right? Yes, so to come back to your question, what if this model isn't appropriate for this type of noise? Then you'll have a talk tomorrow from Alan and Neil to discuss what can be done. And typically we need to do some approximate inference because we can't do exact inference anymore. So we've seen that the choice of the Kernel parameter has an influence on the model. So the length scale was basically telling how quickly the confidence intervals go back to the prior. And so we need to choose these parameters, right? We need to choose a covariance, and I'll come to that later. But even once we have a covariance, we need to choose what are the parameter values. And so one very common tool is to use the maximum likelihood estimations to find the sets of parameters, what should be the variance and what should be the length scale, such that the likelihood of our model is as high as possible given the data. So the likelihood of a distribution or of a model with the density f given some observations is given by this quantity. So maybe I will just draw quickly on the board a simple example of maximum likelihood estimation. So let's say you have samples from a uniform distribution. You're just not sure what are the parameters of this uniform distribution. And the distribution could be either someone like that, or someone like that, or someone like that. So that's distribution A, B, and C. So maximum likelihood tells you that L is equal to the product of your PDF, so that could be A, B, or C, one of these 3 functions, evaluated at your observation points, right? So let's look at what's happening for A. So we are making the product of all these values. So we'll end up with one number, right? If we do the same thing for C, we are going to make the product of these values, but also these guys in here, where the PDF is equal to 0. So the likelihood of C is going to be 0, just because it's not possible that these observations are coming from this model, right? So we can get rid, maximum likelihood are going to be. No, you shouldn't pick the model C. It's not something that is possible. And if you make, now if we compare A and B, we're going to find that the product of all these values is going to be higher than the product of these values, right? So maximum likelihood is telling us you should favor the model B because it is more likely given the data you have so far. It explains the data you have better. So we can do the exact same thing for our Gaussian process. So we have a distribution that is given by our prior. We have some data, and we can use maximum likelihood estimation to find the parameters of our distribution, so the variance and the length scale, that makes our data as probable as possible. Okay? The only difference we have between the case in our GP and this example is that here I had several observations from the same random variable. And in the GP case, we typically have a vector of n observations like that, but this should be seen as one observation in an n-dimensional space. All right, so our maximum likelihood estimation, instead of making the products of the density evaluated at our observation, it's just going to be the density evaluated at our observation that is a vector. So I can make a graph in 2 dimensions, see what's happening. Let's say we just have 2 observation points. So this is in the x f of x space. This, if this is x1, x2, I can map that to f of x1, f of x2 space. Now I have a 2-dimensional space with only one observation. And in this space, I have a multivariate Gaussian distribution, and I can find the parameters of this multivariate Gaussian distribution that will explain, that will put the mole mass for this data. So if I can, I probably would like to tilt this density a bit, and I would like to change the variance. So maybe if I can find parameters like that, that can give me the best values of the parameter to explain this particular data set, right? That's what we do when we do maximum likelihood estimation for Gaussian processes. Right? So this was just like a drawing with the hand to understand what's happening. Now if we look at, in practice, what we need to do, so we have our likelihood that is a function of the kernel parameter, but it can also be a function of the observation noise that we've seen before, if we don't want our model to interpolate. And we just need to evaluate this quantity where k here depends on these kernel parameters. So this is the bit that is expensive when you're training Gaussian process model, because typically you're going to do some gradient descent to optimize this function and find the best value for these parameters. But at each step of the gradient descent, you'll need to compute this determinant, and you need to compute the Cholesky of this matrix. Right, so for each step of the optimization, you have one matrix inverse or one Cholesky to compute. Yes?
I'm looking at the figure you drew here.
Yeah.
And this is mostly constrained by the fact that we've chosen the mean function of 0 here, right?
Yes.
So, I mean, there's 2 ways it seems that the length scale and parameters will be soaking up a lot of this, where it could just be if you chose a mean function that was
exactly
separate, the fit would be different.
Exactly. So why we don't choose the mean, or why we are careful with the way we choose the mean, is that if you start choosing the mean, it's too simple to say, oh, I found exactly the right distribution, but your mean here is just going to be a vector of parameters. So your prediction, you're going to say, oh, I know it goes here and there, but you don't have any clue about what's happening in there. So you can't really choose just a mean vector. You need to choose a mean function. And the mean function will give you some constraints. And maybe if you say, oh, I know that the mean function is going to be something linear, then you can't actually pick this point. But you can move around, but you will still have constraint that makes impossible like to fit exactly the data with just one Dirac delta function. Yep.
I did have a question about how many unknowns we have, and so kind of how many degrees of freedom and how many observations.
Yes.
So here we have, even if we tether the mean at 0, we still have 3 parameters to estimate.
Three or more, because if you have more than a one-dimensional input space, you can have one length scale parameter per dimension.
Right. So even if I'm not estimating the, okay, you see. So how do we estimate 3 parameters with that 2?
Same thing. So you will, I don't know how much data you have, but like it would not be realistic to build a model with less than 10 observations or something like that. So you're going to have typically hundreds, a few thousand observations, and then you need to estimate a handful of parameters. So we are not too concerned by this ratio so far.
I mean, in this particular example, the 2-dimensional example, how many parameters do we have to estimate with the mean?
2 parameters.
2, okay.
So without the mean, 2 parameters, the variance and the length scale of the Gaussian process. But this is a very toy example, right? I would not in practice estimate these parameters if I just have 2 observations of my GP. Or I would need to have some priors on these parameters, and then I can do some Bayesian inference using these prior. So now we've seen how to build model, how to estimate the kernel parameters, and we need to know if the model we've built makes sense or not, right? So don't stop like, oh, I have a model, I can make my predictions and answer my problem. Make sure your model makes sense, so that's the model validation. So our model predicts a lot of things, right? It gives us a mean prediction, so we should make sure our mean prediction is accurate. The model gives us like confidence intervals, so do these confidence intervals, are they realistic? But the model also specifies a full distribution, so we have covariances between these points. For example, these 3 points are related according to our model. So is this posterior covariance that is predicted accurate? So if we want to just look at the mean, we can use like classic criterions to assess the quantity. So typically you have a test set of new points, and you compare the value you have on your test sets minus what has been predicted by your model. You square that and you take the average of it. That's a usual mean square error. This is more or less the same criterion, but that has been normalized so that we have something that is typically between 0 and 1. When this is 1, it means that the error in here is very small, so it means the model is very good, right? And this is a bit nicer to interpret because it has been normalized basically by the variance you have in your data set. So that can be seen as the percentage of variance that is explained by your model. So if we look at this example in here, we end up with a mean square error that is 0.038 and a Q-square criterion that is 0.95. So that's not too bad. We explain 95% of the variance we have in our test set with our model. Now, according to our model, our vector of observations, it should be distributed as the posterior distribution predicted by the model, right? So it should have this mean value and this covariance matrix. So if you take your observation, if you subtract the mean value, and if you multiply by the inverse of the Cholesky of the covariance matrix, that should take these values that are correlated and transform them into uncorrelated Gaussian random variables, because they are uncorrelated and they should all be standard normal and independent. They should have 0 mean because you just subtracted the mean, and they should have no correlations because you just multiply by the inverse of the Cholesky, which is the operation you need to remove all correlation into a vector. So now that you obtain these guys, you can look according to your model, they should be exactly n01. So you can plot an histogram of them, or quantile plot, or do some normality test to it if you want to. But that's something you can dig a bit into to make sure the predictions given by your model make sense. Here it's not a strong mix match, right, between these two guys who are quite happy about these two things, and we can say, okay, no, I'm happy with my model, I can use it for further steps, or I can measure how unhappy I am and then decide for the application I had, for the application at hand, is it enough to answer the question I need to answer? Yes?
Sorry, what's on the axes of the plot on the right?
So that's the theoretical quantiles of a normal distribution, and that's the empirical quantiles you have for this random variable. So if they are on a line, like they should be on the identity line, and if they deviate, so you can see the tails here. The tails deviate a bit. Like it's just a couple of points. We don't worry too much. But if you do that for a distribution that is clearly not normally distributed, then you'll see something wrong in there. Yes. No. No. So the thing is, most of the time we have limited data because acquiring the data is something that is costly. So you can't just fit a model and then get more data for a test set. So you need to reuse the data you have used for fitting the model. So you can do leave one out to assess the quality of the model. So the first step is to build a model with all the observations except one, and then you compute the model error at this point. So that's very simple to illustrate. That's a model we have. That's the model we want to test. So we remove the first observation from the model. So we fit a model again just without this guy. And then we can look at if the mean is far away and if these confidence intervals we have here make sense or not. And we can do that for all the points we have in our data set, or like a large enough subset of points in the data set, and use these to compute a mean square error and to use the normalized error. So you take this error and you divide by the error that is predicted by the model uncertainty. And again, you can look at quantile plot or just histograms of them. Yes? So that's a very good question. On the paper, if you look at that, you need to, each time you take a point, to invert a covariance matrix that is based on all the other points. The thing is, if you have the inverse of the full matrix, you have like rank 1 downgrade for the computation of the inverse, and it's actually not as costly. You don't have to compute n inverse that are n cube. You just use one n cube inverse, and then it's very cheap to get the inverse of a subset. So yeah, it can be done efficiently. Okay, and now comes the part on the choosing the covariance. So if you have the same data, but if you change the kernel you have in your model, yes?
Is this approach for efficient cross-validation error implemented in some libraries for Gaussian processes?
Yeah. So for the Python libraries, I know they don't implement it. If you look at die stringing in R, the leave one out cross-validation is already implemented.
So Python, no?
Not that I'm aware of. If I'm wrong, someone can. No, no one is. It's not difficult to implement. Okay, so if you change for the same data, if you change the covariance, you're changing completely what are the predictions of your model. And that makes a lot of sense, because if you change the kernel, you change the prior you have on the function you want to approximate. So we should pay a lot of attention when you choose covariances to put as much information as we can into the model. So there's no model, for these two guys, there's no model that is better or worse than the other. This model is better if your data comes from someone like that, and the other one is better if your data comes from someone like that. There's no kernel that is intrinsically better than others. So the question, when someone gives you some data, you should try to get as much information as you can. So for example, do you expect this to be stationary? Like, if I were to shift the data in space, should that change something in the model I'm doing? And if you're stationary, if things only depend on distance, then moving data around should not affect your model, right? You can sometimes get information about the differentiability of the phenomenon you want to approximate. Sometimes things are very smooth. I don't know if you're modeling a temperature, it comes from the heat equation, so you're expecting the solution to be smooth, right? So you should choose a covariance that is smooth according to this information you have from the physics. Do you have specific trends or patterns in your data? So sometimes people can tell you that, oh, there's periodicity, or I know this data I've observed is actually the sum of two things, and this one has this property and this other has other properties. So try to get as much information as possible. And what's very common to do is just to, if you don't have information, it's just to try a lot of different covariances to assess the model quality each time, and then to pick the one that is better in the end. And something that is interesting is also to do some remapping either of the input space or of the output space. So try to change the X location into these things. Why can that be useful? Many of the kernels we have on the shelf are stationary covariances. So sometimes making this transformation into the input space allows to make the data look more stationary. And similarly, if you do this kind of transformation for the Y values, sometimes data is not Gaussian. I don't know, if something is positive, you can't say that a Gaussian is positive, right? A Gaussian has mass everywhere on R. But if you have something that is positive, then you take its log, and all of a sudden you have something that has values on R, and maybe it's more likely that the assumption that the data after going through a log transform is Gaussian is better than making no transformations at all. So yeah, when you're building model, it's interesting to do some rescaling, nonlinear rescaling of the input space and output space. I'm a bit short on time, so I'm going to skip these bits on the Buchner theorem, and I'm going to jump directly to this. So if you, yes?
So is GPs bad at modeling periodic data or something?
No, it's good at modeling periodic data. Okay. Yeah, you can. So we've seen previously that we have covariances that lead to a periodic sample path. So that's exactly what you want. Like, you can use this as your prior information. So making new from old is, even if it's sometimes difficult to design new covariances, we can take existing covariances and combine them in a lot of different ways to make our model more expressive. And this is what this is about. So if you take two kernels, K1 and K2, and if you sum them together, then you end up with something that will still be symmetric and positive definite. So you can use this in a model. Now, if you take two kernels that are defined on different spaces, you can also sum them together and get a valid covariance function on the joint space. And similarly, you can also make products of covariances, and you can compose them with a function. So let's see how this can be useful. So that's just what I was saying. If you sum two kernels, you still end up with something that is a valid covariance structure. So here's an example. A Maten 1/2 kernel plus a linear kernel. I end up with something here that I know I can use as a covariance. And from the GP point of view, this sum of covariances can be seen or should be interpreted as the GP, where the sample path are the sum of the sample path of these two covariances. So same as before, if I have a Maten 1/2 kernel plus a linear kernel, the sample path are going to look something like that. So I can either get these guys by summing these, or I can get these guys by sampling from these covariance, right? It's completely equivalent to say, oh, I'm summing covariances or I'm summing processes. So here's an example that's from GPML to show how this can be useful. So that's the data set we have. It's the CO2 concentration in the atmosphere. It looks like it's plotted here as a curve, but again, we have 1 point every month, so it's exactly as before, right? It's just a set of a lot of points we have so far. So we can try to fit this data with a squared exponential kernel, and you basically have two choices when it comes to these parameters. You can either say that the length scale has to be very short because you have some like high frequency variations in your signal, but that leads to a very poor model, because as soon as you're not that far from the data, your model say, oh, I know that the underlying GP is very, very wiggly, so I'm too far from the data to predict anything, and I'm going to come back to the prior distribution. So here the confidence interval is kind of right, but the mean is completely wrong. On the other hand, you can say, oh, I definitely have a trend, so that's something that is low frequency, so I want to have large length scale for this model. And if you fit the model, you end up with something like that, which is also wrong. Maybe the mean here makes sense, but the confidence intervals are completely wrong. So the thing you can do is you can sum these two covariances together. It's like saying, I see this signal as a sum of like a large trend plus some high frequency variations on top of it. And that's the kind of model you end up with. And now it starts to make sense. Just because we've given the model the right building block, saying, I know there's both low frequency and high frequency in there, then you end up with a model that's great. So the model is great, but we can do even better. So we do have some periodicity in here. So the CO2 concentration is higher during the summer than it is during winter. So these variations, they have exactly a 1 year period. So in our model, we can include a periodic kernel in there, and we can also say, unfortunately, I know there's a trend going up, and I believe this trend is something quadratic. So we can put this trend into the covariance, or we can put this trend into the mean of the model. It turns out to be almost equivalent, and that's the kind of model we end up with. And now that's kind of a good model that makes sense, and we haven't done anything crazy. We've just analyzed the signal a bit and say, this should be the right building block. And all these covariants here, they will depend on their own length scale and variance parameters, and they are all estimated jointly with maximum likelihood estimation. Yes?
When you said putting it into the mean versus putting it into the covariance structure, it's almost equivalent. Can you elaborate on the almost part?
So it is equivalent if you put it inside the covariance and you put a very large variance to it. When you have things into the mean function, they are not their complexity is not penalized into the maximum likelihood estimation. So you can very well estimate like very high values for constant and things like that. When you put things into the covariance, then you have some penalty that come to it because of the determinant term you have in front. And the higher the variance is, the lower the penalty you put. So in the limit of a very large variance, then the two models are exactly the same. Right? Yes?
You can also combine two stationary kernels to produce a non-stationary kernel.
So if you sum two stationary covariances, you will still end up with something that is stationary. Yeah, I don't think they just sum them or multiply them. So you can do things with like change points or things like that. Maybe that's what they're doing.
Use a weighted combination of the kernels where the weights change with space to make non-stationary. That might be.
Yeah.
Yeah, right. That makes sense.
Good point. So that if you sum covariances that are defined on two different spaces, so we have one covariance defined over the first variable, a second covariance defined over the second variable, and we use it to make a covariance defined over the full space in HIT. So once again, this can be seen as the sum of two GPs, one over x1 and the other one over over x2, and that's a GP over a two-dimensional space. So that's some samples from this two-dimensional GP. So you can see these samples, they have some very specific property. They are additive functions, just because of this interpretation we have in the background, right? So you can either sum these guys or sample from the covariance, and the model will know just from the covariance that things are additive. So this is great if you want to approximate additive function, of course, because you're giving a lot and a lot of information by saying, oh, I have this data and I know it comes from an additive function. Like you rule out a huge number of functions that are not additive, so your model will be much, much more accurate. And yeah, and you can also build model over high-dimensional input spaces. I'll come to that in a minute. So what happens if your kernel is a sum of covariances? Then you can, when you predict M, so that's the usual expression. I've just shown here that K is actually a sum of two guys. And now if I expand the product with the sum, then I end up with the sum of these two guys. And these two guys, they can both be interpreted as conditional expectation, right? The first one, M1, is the conditional expectation of Z1, given that I observe Z1 corrupted by some noise that is Z2, right? So when you sum covariances, you can still interpret sub-block of the model. So that can be quite convenient. And if we look at the variance of a model with an additive kernel, a two-dimensional additive kernel, we end up, so maybe if we look at a classic variance of a two-dimensional model, so we can see that around observation points, the variance is equal to 0, or at least is small, but when you go away from the observation point, the variance increases. And that's what we get for an additive model, and we have some locations where we don't have observations, but the variance is small. Can you tell why? So remember, we are using here an additive covariance. So we are telling the model, we know the function we are modeling is additive, so we know that the difference, like this minus that, should be the same as this minus that. So knowing the value of an additive function here, here, and there, so kind of on the three summits of a rectangle, actually gives you the value in here. So the model is sure of what's the actual value there, just because it has these three observations and it knows that the function is additive, right? So, so all kernels are symmetric. No, I don't see the symmetry playing a part here. We can come back to it later if you want. So this property can be used to build model in high dimensions. So we know, because of the curse of dimensionality, we know that the number of observation points, if you want to cover high dimensional space, should grow exponentially with the number of observations. But additive models are popular in high dimension just because they break this curse of dimensionality. If you just observe values like on the axis and you know your function is additive, you're basically going to know your function everywhere. And the GP model knows that. So that's why additive kernels can be used for high-dimensional input spaces. So we can also make the products of covariances, but I'm not going to discuss it too much. That's the product of Gaussian and the product of a cosine covariance, and we end up with something like that. So here you can see that the value here is negative, so the point here and there are negatively correlated. That does not violate the fact that this covariance is positive definite, right? It's very different to be positive definite and not taking negative values. So if you sample from this covariance, no, I don't have the sampling here, but you will tend to have functions that are wiggly. They are not exactly periodic, but they are wiggly, that they behave like waves. So we can make also product of covariances over the same space. We can combine a kernel with a function. So if this guy is a valid covariance, you can pick more or less any function f in here, and that will still define a valid covariance. And this covariance can be interpreted as the covariance of a GP that is Z1 evaluated at f of x. And yeah, so that can be seen as a nonlinear rescaling of the input space. What we had before with the length scale is just we're picking f of x was x over theta. But you can pick other types of transformation that are nonlinear if you want. And that's the kind of things you can get if you take these covariance and the transformation 1 over x, points that are like close by in this space. After transformation through the 1 over x, they will appear to be very far one from another. So we get samples that are very wiggly in here, and that becomes more and more smooth with time. Right, so here we started from a stationary covariance, and we made it non-stationary. And yeah, and of course, these transformations, they can be combined. Why is this guy a valid covariance? Because this can be seen as the product of a linear kernel remapped through a function f times another covariance. Yeah.
And the function f has to be some sort of function or any function?
No, it can be any function. And yes, and can we automate? So we've seen we can make sums, products of covariances. We have a lot of covariances. Can we automate this choice of the covariance? And that's quite an active area of research, like especially in the group in Cambridge at the engineering department. So the method they propose is, they call it the automatic statistician. So you start from a collection of kernel functions. It's basically the kernel function we've been discussing so far. Most of them are stationary covariances, and some combinations you can have between the different covariances. And then they use a greedy approach by trying to add new covariances or multiply by new covariances, or substitute one of the covariants they have in their model by another covariance they have in the model. And they look at the one that has the highest value of this criterion. So maybe that will answer the question you had previously. Previously, I was just talking about estimating the parameter with the maximum likelihood, that is this quantity over here. The thing is, when you compare models that don't have the same number of parameters, these likelihoods, you can't compare them directly anymore, because a model with more parameters will have more flexibility, and typically will do better when you just look at the maximum likelihood. So the base information criteria is something that will penalize the model by the number of parameters you have in it. And this penalty depends on the number of data points you also have. So if you start comparing different models, it makes more sense to use the BIC rather than just the maximum likelihood. And yeah, and the automatic statistician also generates human readable report, because if you have if your covariance is a sum, then you can say, oh, I believe that my signal is a sum of different components, that each component, for example, if you have one periodic component is a sum, you can say the first component behaves periodically with a period of 1 year, as we've seen in the Mona Lisa. But the structure of the kernel is something you can describe as structure you have in your data. And yes, and I think I just have 5 minutes. I'll cover that and just the conclusion. I'll skip one part. So that's another way where you can design covariance function is by mapping the GP through a linear transformation. So we've seen GP and linearity, they fit very well together. If you modify linearly a GP, then you still end up with something that is a GP. So typically linear operators, they will commute with the covariance. So here's an example. You know that the function you want to approximate is something that is symmetric. So you can find a transformation that to any function will return a function that is symmetric. So to f, you associate f of x if x is smaller than 0.5, and f of 1 minus x is greater than 0.5. So that's one way to make a function symmetric. Another way to make a function symmetric is just to average the value on each side of the symmetry 0.5. Yes?
Yes, sir. What's Lx or y? So, you mean, yeah, could you please
in here or in there?
No, in the property.
In the?
Yeah, and what does it mean to commute with covariance?
To?
What does it mean to commute with covariance?
Here, for example, consider this guy. If you, so that's L of f, right? If you have the covariance between L of f the covariance of a sum is the sum of the covariances. So I can say this is the covariance of f plus the covariance of f of 1 minus x. So that can be seen as L, like as an operator function of a f applies to the covariance between f of x and this guy is still there, right? So that's what happens if you sample from these covariances. So here we can see that we've broken the differentiability of the GP in 0. That's just because our linear transform did this. But this guy preserved the differentiability in 0, just because it was kind of a smarter way to make the sample path symmetric. And now if you have data over here, if you have one observation here, then in your posterior distribution, you will have a 0 variance in there, just because the model knows, like everything in the prior is symmetric. So if you observe one value on the right, you should have the exact same value on the left. Yes?
How rich is this space of linear operators? I mean, so there's maybe the H group, for example?
Yes. Yeah.
Because you can do quite a lot of this.
Yeah. The kind of thing you can't do is you can't find a linear operator that will take a function and make it positive, for example. This is not something that can be done linearly, or to make it monotonic, things like that. There's no such linear operators. But things as symmetry, additive, extracting the periodic components, like all the things that are projections, basically, that works very well. So yeah, so we have linear operators that can take a function and make it symmetric. We can build many operators that will do that, and the question is if one of them actually optimal for the GP we have. Can we extract optimally what's the symmetry component of a sample path? And that's something that sometime we can answer, but that really depends on the covariance function. So that's a very interesting question. I'm going to skip this part and sensitivity analysis and just jump to the conclusion. So the various step for building Gaussian process regression model is to get the data. So sometime if you're modeling like statistics, you get to choose the data you actually get. So you need to choose in which location you want to evaluate your GP, for example. And you sometimes can choose, you have a maximum budget of observations, so you have to choose carefully the points. What will be the points that will help you getting the best model in the end? In machine learning, most of the time you're given some data and you have to deal with it. Then you choose the covariance. So can you list all the things you know, and of all these properties, can you incorporate this information into your model, typically into the kernel, but also sometimes into the mean function. An example where it's good to have information into the mean function, if someone, for example, runs an expensive numerical simulator to give you some output, but he also has a simulator with a numerical simulator with simplified physics in it that runs very quickly, but that is going just to give an approximate of the actual quantity you're interested in. It can be interesting to use this first approximation as the mean for your model in approximating the second one, right? Things like that, all of these kind of informations are interesting. Then you can estimate the parameters, typically with maximum likelihood. You can do cross-validation. I haven't discussed about it, but multi-start is something that is interesting. Sometime in the maximum likelihood, you have local minimum, so it's interesting just to start the optimizers in different places just to make sure you end up with the best model you can. And then validate the model with a test set or leave one out. And typically, you iterate over these steps, right? And in practice, you may get errors like the choice key decomposition failed or the metric is not positive definite. So that typically comes from points that are too close one to another, either the length scale are very large, or you're having a GP with a lot of smoothness in it. And so sometimes you can reduce the smoothness, or if you have points that are close by but they give the exact same information, you can also remove some of the points without losing actually any information. And yes, so in order to avoid these numerical problems, it's quite common to add a small observation noise, something very small like 1 in 10 to the minus 6 or something like that. It just makes the matrix much better condition, and it doesn't really change the model you end up with. Yeah, and impose some bounds on the length scale parameters or minimum noise variance, and try not using covariances. Richard said not to say Gaussian square exponential covariance in here, because you have a lot of smoothness, so you run much more quickly into numerical issues. And that's it. Any question? Yeah.
So you talked a lot about the maximum likelihood to find the optimal kernel parameters.
Yes.
Right? But the kernel kind of appears in the equation, you know, in the denominator and determinants inverse and so on. So
Yeah.
I guess it's not a convex optimization problem.
No, it's not.
And so I guess depends a lot on initialization and all these sort of things.
Yeah, that's why multi-start is a good practice.
Okay, so is there some sort of guideline on how to choose initial kernel parameters before optimizing them, or if there's like some general purpose values that we can choose according to some rule of thumb or something like that?
So you can, since you have a model where if you're in low dimension, you can plot the sample path. You can wonder what sample path would be realistic. And if your sample path is like 10 times, if your length scale is 10 times larger than the input space, your sample paths are just going to look like constant or like linear things. Does this make sense? No, not really, right? So starting with a length scale that is rather small is good practice. And I don't know, I usually normalize the data to make it everything on 0, 1, and I start like with a length scale of 0.2 or something like that. I'm going to have a few wiggles in there. Let's see how it goes.
So data normalization also is important.
Yeah. Great, thank you very much.